Hi guys, Miss O'Connell here. So we're going to start out quickly talking about our plan for the week and into next week. So today we're going to be talking about angular velocity. You're going to watch this video, obviously, and then there's a certification quiz, which I'll talk about at the end. Tomorrow we're going to do a cumulative review of all information from uniform circular motion, and then you'll have a study guide type activity to complete. On Wednesday, we'll have a mandatory Google Meet. As per usual, there are no school pickups this week. So if you cannot attend for a specific reason, you need to let me know beforehand. It's the last mandatory Google Meet, and it counts as a grade. On Thursday, you will be given your circular motion assessment choice board, and you will choose how you would like to be assessed for this unit. Okay, and then on Friday, there will be an optional Google Meet to discuss questions, project ideas, etc. In addition to further directions about the individual meetings, which will take place the following week. Okay, and just a reminder that June 12th is the end of the marking period, so all of your work must be completed and submitted before then. Okay, so let's take a look at angular velocity. So we know a little bit about it from our first Edpuzzle video, in addition to the activity that we completed in class on Thursday. So angular velocity explains the rate of rotation of an object that circles or orbits in a particular situation. So it's basically the rate at which it rotates in radians per second. So it's the amount of radians, or the theta, that is covered in a specific amount of time. And that time we measure in seconds. So the rate of rotation of a circling object, we use the Greek variable omega to represent it. Okay, it kind of looks like a curly W. Okay, but that is a lowercase omega. Okay, our units are radians per second. So it's the rate at which an object rotates. How many degrees per second, how many radians per second, how many revolutions per second are covered. Okay, so all of those measurements, degrees, revolutions, radians, all describe a change in angular position, a change in theta, which we use to determine the rate of its rotation. The units that we most commonly need are radians per second. Okay, so as I previously stated, right, the rate of rotation is the number of radians covered per second. So our first equation to describe angular velocity is the change in angular position, delta theta, measured in radians, divided by the time it takes the object to make that rotation. So omega is equal to delta theta over time, where delta theta must be measured in radians, time must be measured in seconds, and omega will be measured in radians per second. We have a few other relationships that help us model angular velocity, specifically how we can relate angular velocity to linear velocity. We have been calling linear velocity thus far the tangential velocity, which is the velocity or the speed of the object as it circles around its path of motion. Okay, and if you remember, that velocity vector, which is represented up here, is tangent to the circular path. Okay, so that velocity vector is tangent to the circular path. So omega is the rate of rotation. So it's how many degrees are covered in a specific amount of time. The angular velocity is the arc length covered over a certain amount of time, or we previously denoted this as 2 times pi times r divided by the period. Okay, so v is the linear speed an object has when it moves around a circular path. The rate at which an object rotates is its angular velocity. Okay, so another way in which we can look at the linear velocity would be the arc length, the linear distance covered over a specific time interval. We know that arc length can be determined by multiplying the radius of the circle, the distance from the center to the path, by the change in its angular position. So we just substituted that into the equation for tangential velocity. So now we have that tangential velocity is equal to the radius times the change in the angular position. You might notice here that now we have delta theta over t, the change in angular position over time, which is defined as the angular velocity. So what we can do is plug in for omega. Omega is delta theta over time. Okay, so this gives us a relationship that relates this linear velocity that we've been looking at to the angular velocity. Okay, so our linear velocity is equal to the angular velocity multiplied by the radius. So the rate of rotation multiplied by the radius. We will get the tangential velocity in meters per second. Or if we want the angular velocity and we have the linear velocity, we can divide that linear velocity by the radius to find the rate of rotation, omega. Okay, so here are two. We have three total. So 2 here on the bottom. V equals omega times r. Omega equals V over r. And omega is delta theta over time. All right, so let's take a look at a few examples where we've used these relationships. Okay, so our first example, we have a toy buggy, so one of those tumble buggies, tied to a string. It's moving in a circle and it completes one rotation every 5 seconds. We want the angular velocity in revolutions per second, revolutions per minute, RPM, degrees per second, and radians per second. Okay, so we know that delta theta, the change in angular position, if it makes one rotation, that means that delta theta is equal to 1 revolution. It makes one revolution in 5 seconds, so our time interval here, which is also our period in this case, is equal to 5 seconds. And we're looking for omega. Okay, so first, so this is example 1, part A. In number 1 of part A, we want revolutions per second. So you know that omega is a change in angular position over the change in time. We're asked to find the rate of rotation in revolutions per second. So we're going to plug in for delta theta in terms of revolutions, which is 1, divided by the time it takes to complete that change in angular position, which is 5 seconds. And we find that the angular velocity is 0.2 revolutions per second. So it makes 0.2 of a revolution in every second. Okay, in number 2 of part A, we want to find the same rate, but in revolutions per minute. RPM stands for revolutions per minute. We most commonly use those units to measure the rate in which motors rotate. Okay, so we have to convert seconds to minutes, as we can see over here on the left-hand side. So we need to divide by 60 and multiply by 1. Our seconds cancel out. We're left with just minutes. So 5 seconds would be 0.08333 minutes. So to get revolutions per minute, we're going to divide 1 revolution by 0.0833 minutes. And we get 12.04 revolutions per minute. Okay, so it makes 12 complete revolutions every 60 seconds, every minute. Okay, 3, we want degrees per second. So we need to convert our angular position from revolutions to degrees. Okay, which of course is not showing up right now. There we go. Okay, so if we have 1 revolution, right, we know there are 360 degrees in 1 revolution. Our revolutions will cancel. We'll be left with 360 degrees. So we're going to take that angular position of 360 degrees, divide by 5 seconds. Oh, gotta change that. That's wrong. There we go. So we're going to take 360 degrees and divide by 5 seconds. We get 72 degrees per second. So the buggy rotates or changes its angular position by 72 degrees every second. Okay, last unit conversion, we need the rate of rotation in radians per second. So we're going to convert revolutions to radians. Okay, we got 2 pi radians. We divide 2 pi radians by the time, which is 5 seconds, and we get 1.26 radians per second. This is our angular velocity. Okay, so now that we have angular velocity, let's say that in part B, example 1, part B, the circle has a radius of 12 meters. Okay, we want the object's speed, its tangential velocity. Okay, so we know that omega from our previous part is 1.26 radians per second. Okay, so it can cover 1.26 radians each second. We're told the radius of the circle is 12 meters, and we want the tangential velocity. We know that the tangential velocity is equal to omega, the rate of rotation, times the radius. So we multiply our rate of rotation, 1.26 radians per second, times 12 meters. We know that radians is an implicit unit, so we multiply meters times radians. Our radians are assumed, and we do not write them. Okay, so our value here is 15.12 meters per second. Is the speed, the tangential velocity of the buggy as it rotates. Its rate of rotation is 1.26 radians per second. Okay, let's try one more example. So example 2, we have a rotating crankshaft, okay, which is located within an engine. This object right here is our crankshaft. It kind of looks like a disc rotating around a axis here. We're told that the length of the crankshaft is 4 centimeters. So that means that the diameter is 4. The radius would be half of that. It'd be 2 centimeters. We know that we use meters in physics, not centimeters. So we need to convert from centimeters to meters. We're told that the rate of rotation, omega, our angular velocity, is 2,400 revolutions per minute. We want the speed, the tangential velocity, of a point on the surface of the crankshaft. So we're looking for our velocity, we know our radius, and we're given omega in revolutions per minute. We know that omega needs to be measured in radians per second. So the first thing we need to do here is convert. So if I have revolutions per minute, to get rid of the revolutions, I need revolutions in the denominator, so they cancel out like variables. So I'm going to multiply by 2 pi, divide by 1 revolution. To get the meters out of the denominator, the minutes out of the denominator, I want minutes in the numerator. So I'm going to multiply by 1 minute and divide by 60 seconds. To find that our angular velocity in radians per second is 251. Okay, So we have the rate of rotation and the radius. We're looking for the tangential velocity. We know that the tangential velocity is equal to the tangential velocity is equal to the angular velocity times our radius. Okay, so we're going to take our tangential velocity, set it equal to omega, which we calculated to be 251 radians per second, and we multiply by our radius, okay, which is 0.02 meters, to get our velocity, which is 5.02 meters per second. Okay, so we're going to head to now is the certification quiz, which, when you finish, it'll give you a congratulations certificate. You do not need to attach it anywhere. It's going to send me an email of your certificate to prove that you completed it. If you do not correctly answer all the questions, it will force you to keep going until you answer the questions correctly. Okay, so it'll make you retry a question until you get it correct. Okay, if you have any issues, send me an email, and I will talk to you guys tomorrow.